Hello, and welcome back to the Strangewater podcast. Thank you for joining us for today's conversation. There is a lot to love about zero knowledge cryptography. On this show, we really only focus on using ZK as a tool to compress computation and to enable decentralized computing networks. But we could easily spend just as much time on ZK's implication for privacy or digital identity or any of the undiscovered applications that we're inevitably going to find for ZK. We already see so much promise, and we're in a world where groundbreaking research is released faster than Apple can get out a new iPhone. But behind all the optimism and the entrepreneurial energy behind ZK today, there's a more frustrating side of the technology. The concepts are impenetrable, and the tooling is hard to find and even harder to use. And what few primitives that do exist are a nightmare to integrate. And really, that's just the start. Again, it can be frustrating, but I guess that's always the case when you're deploying research hot off the forge. But we are here today to focus on one particular pain point: performance. Even the best ZK systems right now take so long to run that they're practically useless in real-world applications. Just like the internet would be functionally useless and largely ignored if we could only transfer one or two sentences in like an hour, we would be in trouble if the performance of ZK systems was limited to what we had today. Today's guest is Leo Fan, founder of Cysic, and a big reason why the ZK community is so confident that we will overcome the performance problem that we are racing to build empires here. Cysic is working on creating hardware specifically etched with the ZK primitives that will power our trustless future. This episode is a comprehensive look at what it means to write applications into silicon and metal, including an overview of how chips are made and reflections on how chip manufacturing factors into geopolitics. I won't spoil the numbers for you here, but suffice it to say that once you hear Leo tell us how dramatically they can already accelerate ZK proofs, you'll begin to understand just how it feels to be at the beginning of ZK's Moore's Law frenzy. One more thing before we begin: please do not take financial advice from this or any podcast. Ethereum and ZK will change the world one day, but you can easily lose all of your money between now and then. All right, let's go. Leo, thank you so much for joining us for the Strangewater podcast.
Thanks a lot for having me here. Yeah.
Of course. So before we dive into ZK and get into hardware, I'm a huge believer that the most important part of every conversation are the people involved. So with that as background, can you give us a little bit about who you are, how you found ZK, how you found hardware, and just tell us a little bit about yourself.
Thanks a lot. Yeah. So my name is Leo Fan. I'm a co-founder of Cysic, and before Cysic, I got my PhD from Cornell. So from Cornell in cryptography. So I'm more like a software algorithm guy. And before Cornell, I did some time. I indeed spent some time in China doing some Bitcoin mining. And after Cornell, I spent some time in blockchain company called Argument. So when I was at Argument, I helped with Argument state proof. So Argument state proof is essentially a ZK proof, can be used as a cross-chain bridge between Argument and Ethereum, Argument Solana. So when we finished the POC for that part, it was April 2022. I found the post generation time for the ZKP proof there is quite long. I try a lot on the software and the algorithms, but it didn't improve a lot on the proof generation time. So I think maybe we can design some specialized hardware as what we did for the Bitcoin mining before. So we design some specialized hardware for that to make sure the proof generation time is acceptable. Yeah, but I do not yeah, so at that time I didn't know too much about the market, so I talked to my friend in some like ZK companies, and they like promised me like there will be like a huge demand for your hardware if you like succeed in doing that. So that's like why like we started Cysic. So Cysic is um, it's a hardware design company like for ZKP. Like we aim to design the some specialized hardware like the ASIC for to accelerate the proof generation for ZKP. And right now we are in the phase of using FPGAs and also GPUs to do the work. Yeah.
So we'll unpack and like really dig into what it means to be using FPGAs and the roadmap to ASICs and then what that'll mean for the industry. But while we're still in your background here, can you tell us the story of like how you found Bitcoin and why you decided that this was something interesting and not something to run away from?
Right. Actually, kind of like yeah. So like I yeah, before Cornell, like I spent some time in China, also like doing some research on cryptography. Yeah, so like I happen to know a friend like in Japan. His name is actually Okamoto. So like when I first read the Bitcoin white paper, the name's Nakamoto. I think maybe he used a pseudonym like to write that paper. So I read it. It was sometime in 2011, I think, or 2010 or 2011. So it was like a while back. Yeah. So that's why like I know this paper. I think yeah. So like we actually we try to solve like the cryptographers. They try to design some like e-cash long ago, but the previous approach is quite maybe boring, I would say, and this like Santosh, he come up with a very nice idea. I'm not sure if it's he or she or like or they. Yeah. So but they came up with a very nice idea to design this like peer-to-peer like payment network. I thought like that was very very interesting and also it has some relationship with my research and I happen to know someone in China at that time was like doing some Bitcoin mining so like I saw and like joined them like it was like 2011 or 2012 at that time. Yeah.
So I think like today in 2023, it's really, really clear that cryptography and everything that we're working on is like it's so new and we need to like kind of get it right. But once we get it right, it's going to have implications on all sorts of industries and all sorts of computer science problems. I think one of the like more subtle but more cool things about the Bitcoin white paper moment is like that was the moment where maybe not you as a real cryptography researcher, but us on the layer above that, we realized that, oh my God, for the first time that I've ever realized, there's another use case for cryptography other than just encrypting messages like tighter and tighter and tighter. And so I guess like my question for you is in that moment when, you know, your friend who you think might be Satoshi is like exposing you to this and you're getting more and more interested, what percentage would you say attracted you of like the ideological, the decentralized censorship, like those kinds of things? And what part of it like was truly about the tech and implementing cryptography in a way that provides like brand new systems?
Yeah, so I would say the like it's a technique in the paper like first draw my attention. Yeah, so like previously, like people all the design this like e-cash system, they are centralized system. And if people want to decentralize it, there is always a way to circumvent yeah, to get it centralized. Yeah, so like the at least in the very beginning when I saw the Bitcoin white paper, I found it like fascinating due to the techniques to help decentralize this system. Yeah, it was like quite interesting to see that idea. And yeah, and also like maybe after some time, like I realized maybe like the decentralization will also be very helpful for us, like to get around the censorship and all the other things. Yeah, so I would say it was a technique that drew my attention. Then I found maybe the ethos or the idea like in the blockchain community somehow aligns also with maybe some part of me. So like yeah.
Mm-hmm. Yeah, no, that makes sense. And again, while we're still in the background section of this conversation, so you found yourself at Algorand, and I think that you might disagree with this. Feel free to. I think that many of us in this industry really believe that kind of the point of this industry is to build out Ethereum and then build, from like this core shared backbone settlement layer. And I think a huge thing that we saw in the last cycle are these alt L1s, which for me, I don't really see a role for in the long term like story of cryptocurrency and like digital property. But the cool thing about all L1s is they provide a playground and like an entirely different innovation space for like blockchain related stuff that doesn't screw with our like precious Ethereum. So with that kind of as context, like, can you talk a little bit about you found yourself at Algorand? If there's an interesting story of how you found it, let us know. But what did you think that Algorand was doing that was really cool and really interesting that you think is worth, like, that you took with you in the work that you're kind of applying now?
Yeah, so I would like to talk first a little bit about the ICO summer back in 2016, 2017. Yeah, so like I was somehow also involved in that period of time. Yeah, so like all these like layer ones, as you mentioned, they try to come up with a better throughput, like a higher throughput, better efficiency to kill Ethereum. But yeah, as you can see, like I would say like maybe yeah, maybe some of them will have like higher performance over Ethereum, but like in the end, it's all about the community and like the community they can support Ethereum. They will come up with like different depths on Ethereum to enhance it, and Ethereum also itself got like involved, like from the very beginning. So like when I was at Cornell, like actually, we met like so we as a research group like met Vitalik quite often back in 2015 to 2016. There is a like cryptocurrency boot camp at Cornell, and yeah, we somehow like interact with Vitalik at that time. And as you can see, like some of the Cornell professors also come out develop some like neurons, try to beat Ethereum on the efficiency side. And also like the argument is also funded by Silver McCartney, who is a two-year award and also a MIT professor. Yeah, so like actually like I think like we actually we the professors like they bring a lot of the research from the academia to the industry. Yeah, this like for instance, like you can get like higher throughput using some of the techniques like proposed by my advisor in NSHE. And you can use like maybe like VRF to like select the block producer. Like so this idea was like by like Mikami. I guess like maybe the professors like provides like more formally defined and more rigorously proving idea to the world. Maybe some of them are not very efficient, or like when the professors they implement these ideas in the community world, they are not like very good at that. But I would say the input provided by the professors are quite important to the community. Yeah.
Yeah, that makes a lot of sense. So I, it is so clear if you're working in proofs or ZK proofs at all that like Algorand or beyond, like these things are really cool, but it's really, really hard to like get them done, right? And there's all these pieces around the tooling and the frameworks and just like the difficult pieces around getting like advanced moon math into your computer. But then, as is very clear, like there's a whole aspect of performance. So we'll move into this piece now, but just like as a preface, when you're running these proofs and you're seeing that they're running really slow, how much background do you personally have in hardware, and how much do you see in this moment that like hardware is a real answer here? or is that become part of the solution as like socialize and communicate more and more with other people that this is the problem and we need to come up with a solution?
Yeah, so speaking, like I don't have much background in hardware engineering. Like the thing, like I or the like perspective I have for these algorithms is to say like first to how parallel this algorithm can be, and the second part is like the what is the interaction between the processor and the memory during the computation. So like if I can figure out like these two parts, then I can say maybe also like very ad hoc thinking about the hardware friendliness of this algorithm will be. So that's my like first impression on ZK. When I take a look at the ZK algorithm, like I know like there are a lot of algorithms. So I first focus on this like major components, like the multi-scalar multiplication, number theoretic transform, and the Poisson-Merkle tree. I saw like um I guess like maybe the majority of them can be like very parallelizable, like on the processors. And although like some of them have like quite weird memory access patterns, but like we can always using some like shuffle or other techniques to improve on that. And if we can like run this like algorithms in massively parallelizable mode, then we can borrow the idea like we developed for the Bitcoin mining. Like recalling the Bitcoin mining machine, it doesn't it doesn't have just the one chip. It actually has like more than 100 chips in the mining machine to accelerate that. And we can do almost the same thing. Although like we need to deal with the flexibility and also the yeah, so like the ZK skin, like they are not stable yet. So like we need to handle the programmable part also as well.
Got it. So, last question before I ask you just what is Cysic and can you describe me what you're trying to do? But just I think a necessary piece of background is can you help me and help the audience understand, let's just say the spectrum of CPU to FPGA to ASIC and why on that spectrum, like basically what do those different terms mean and why as you move closer to ASIC, do you get more efficiency, but what trade-offs are you making as you move over there?
Okay, yeah. So um, I would say like we will treat the CPU maybe as a like Swiss army knife. It's like very powerful. It can handle a lot of like functionalities. And the FPGA is less powerful with army knife. But it doesn't have that functionality, which means it can be like more focused on doing like maybe it's just something, and you have more ownership on this FPGA. You can program it to do something, and you do not need to waste any resource on the FPGA to do some other functionality that you don't care about. Okay, so that's the FPGA, and the ASIC is basically a hammer. It's a very powerful machine, but it can be used to do only very limited things. It's like yeah, which means um, the clock frequency of the ASIC will be like much higher than FPGA, but it doesn't have too much flexibility inside. It can do one thing or like maybe one or two things like very very well, but it cannot be expanded to do a lot of things.
And so, is it fair to think of if a CPU is the Swiss Army knife, it's general purpose, it can do anything that any computer can do, and an ASIC is a hammer, it is very specific, it can only do one thing. Is it fair to think of an FPGA as like it's a programmable chip that virtually can act like an ASIC, but the cool part is you have the flexibility to change it a little bit. So you get the flexibility and a little bit of the performance, but that's why it sits like right in the middle. So first of all, is that correct?
Yes, that's correct. Yeah, it's right in the middle. And you can basically program the chip to do something like you like, and you don't need to waste the resource on the chip to like yeah, things like in the CPU it always have some it always reserves some resource to do other things. And you can only account for maybe a minority of the CPU chips to do your computation. Yeah.
And again, I think this is so critical to what Cysic is building, so I'm just going to hammer it home. The idea here is that like a CPU, because it's general purpose, has to spend a lot of overhead and a lot of non useful computation setting up the computation that wants to be done, right? So like let's say I want to do 1 plus 2. The CPU first has to say, okay, we're going to do addition. Okay, there's going to be between two digits. Okay, okay, okay. All right, now we're going to do 1 plus 2. Whereas an ASIC has none of this generalizability. All it knows how to do is take an input, take a second input, and do the plus. And if you ever want to do multiplication or division on that chip, you're screwed. Like it's in the silicon that it can only do the addition. But the good news is that is you have zero overhead. And it's that loss of overhead which allows ASICs to like perform basically the same operations, but like orders of magnitude faster than a CPU. Is that correct?
Yes, that's correct. Yeah, so like in the ASIC, you basically like hardwire all these circuits on the chip, and you cannot do something like you haven't planned on the chip. So that's some like limitation on the ASIC. But on the good side, it's like very performant and it's basically can run things like in massive parallelizable way to improve the efficiency and also things like and also it's kind of quite cheap and like yeah compare with like designing or like taping out a CPU. So like you control all the resources on the ASIC chip, like how many pieces like you want to put on the ASIC and how much like memory you want to have on that. So like you can control the budget and like you just tailor something like for yourself and you just pay for oh yeah yeah, you just pay for that.
Yeah. And I definitely want to spend some time talking with you about the manufacturing process. I mean, we live in 2023, like all anyone on a global scale is talking about is chip manufacturing. So we'll get there in a minute. But I think we've got enough background to like, Leo, can you tell us like what is Cysic? What is the goal? And yeah, like what are you trying to do with for ZK technology?
Okay, yeah, so like for Cysic, our end goal is to design some hardware that can generate the ZKP proof in real time. So which means like we want to generate the ZKP proof for all the major proof system and for all the major circuits such as like the ZK event circuits, the ZK ML, the ZK GPT-2, or like some also Poseidon hash circuit in less than 1 second. So that's our goal. And we also want to achieve this goal in a cost-effective way. Yeah, we don't want to like spend maybe a 500,000 to just produce just one machine which is capable to do that. We want to we want to like reduce the cost for that machine to be like comparable with the current the mainstream GPU card, the 4090 or maybe the 5090 GPU card that will be released next year. So that's something that we want to achieve the best performance in a cost-effective way for doing the ZKP proof generation. Yeah, so that's the goal for SESIC.
Cool. And then is the goal for Cysic to be creating chips that are like bought by maybe not consumers, but like for example, I'm someone who's an Ethereum home staker, and so I'm willing to dedicate like home resources to something. Like are Cysic's chips aiming to be in that like kind of dedicated hobbyist market, or are we looking at like the same as like the NVIDIA high end chips, like they really only belong in data centers and like those kinds of chips?
Yeah, yeah, so like so that's something like we want to achieve. We want our machine can be bought actually by like normal individual, not by this like enterprise or like the high-end one. Yeah, so then like we just want to at least replace the majority of the GPU cards that is used in the ZKP proving currently with our machine. Like we since like when people are talking about this like chips or like the mining machine, they have an impression that they could be like very expensive. But actually that's not maybe that's correct for now, but with Cysic chip, we want to change the impression. We want to see if you use our machine to do ZK proofing, like actually you can get your money back in like maybe in a like acceptable period of time. Yeah, so that's something like we want to achieve.
Cool. And I think we can talk a little bit later about what you just said is very interesting because that's circling back the actual hardware you're creating with some of like the interesting crypto economic systems that are being built on the blockchain side. So let's circle back to that. But I think the really cool thing about like what you're building is like the there's a lot of problems with ZK technology today. We've talked about, right? There's the implementation details and then there's the actual performance. And today performance is like so rough that, you know, we're in the dial-up era of like ZK technology, right? Let's focus for a minute on that actual application development and how that marries up with hardware. So the ZK, very, very complicated. Let's take one example like Plonk. Plonk is really like this giant protocol. And in it, there's like a bunch of different things that could be considered ZK. There's a bunch of different things that's just, I don't know, overhead or transformations, let's say. And then like within Plonk, there's a commitment scheme. We'll just use KZG commitments for a second. Within KZG commitment, there's some things that are considered overhead. There's some things that might change in the future. There's some things that won't. And we can keep going all the way down the stack until we get to like the most basic primitives, things like multi matrix multiplications or FFTs, or like the core mathematical primitives. And I guess just to cut to the chase, like my question for you is like when you're looking at holistic ZK systems, how do you think about designing hardware that is like really applicable and can really accelerate these systems, but doesn't tie your users and yourself as a company to like technology that is so quickly changing and like might be outdated within, I don't know, like a week?
Right. Yeah. So as you said, like the ZK, if you like dive it in deeper, you will say like you start with Planck and then you go down to the like polynomial commitment scheme, and then if you choose like maybe KZG, then you go down to like MSN entity, and then you go down to like modular multiplication. Yeah, so like maybe like we try to design something that's like quite general, like I mean like general for the ZKP scheme since they are evolving like so fast. Yeah, and we still want to accelerate it, and but we want to support the mainstream system and the potential updates. So like to handle that, we first need to come up with a vector machine, and this vector machine can basically handle this like vectorized addition, multiplication, and also modular multiplication. And yeah, so based on this based on this vector machine, we have I would say it's firmware part. So like we call it ZK ISA, ZK instruction set architecture. So this architecture, we basically define like several category of instructions. And yeah, so like the instruction there can be like NTT, like MSN, like for the different curves, and NTT for different ways. So like we can basically using the instructions in the ZK ISAM to construct I would say like the major kernel, the MSN, TT, persistent Merkle tree, and all the other things. Yeah, so this will accounts for um, uh, the majority of the current proof system. I mean like in terms of the proving time. But there's still like if you want to accelerate the KP faster, then you need to accelerate every possible component in the KP. Yeah, so the long tail operation is like very complicated to handle, and we are still like working on that. So some potential ideas to say like we can have some like CPU, like by CPU I mean like the ARM CPU cores on our chip to handle this like long tail operation. Yeah, since like you want to have a very satisfying performance, but you do not want your like maybe your PCBs to be plugged into some other ones like servers. since the communication between these like two things might be like the bottleneck in the whole ZK proof generation. You want to achieve the you will want to have all the things like all the computation happen on chip to save some bandwidth there. Yeah, as we also mentioned like in our Twitter, like we observe that the major bottleneck actually in lots of like ZKP component is a bandwidth. Yeah, so like if we can somehow avoid that, then we can also have like better performance. So that's some rough idea. So like in summary, like for the major components, the previously major component, we have a clear solution. But for the long tail ones, like if we want to have all the computation happen on chip, like we are still exploring the solution for that.
Mhm. Got it. So just let me repeat it just to make sure I understand it. What you're saying is that it is correct to think about the ZK system as deconstructed down to the base mathematical primitives, and those are like super, super acceleratable. You've already kind of figured them out. What you're starting to realize is that the new, or maybe the original bottlenecks of this system are they're not really about the actual mathematical primitives, the FFTs that you're running, anything like that. It's turning out that the bottlenecks are in the latency and the bandwidth of just like moving all the data to the correct chip or the correct part of the process. And what you're finding now is that the opportunity is to build these more integrated chips that contain like an FFT ASIC portion, but also might contain some other portions to accelerate the whole process and not just the advanced math.
Right. Yeah. Previously, like if you running the KZG KZG Plunk, like say using Hello 2 as a software backend, the the MSN entity accounts for 60 to 70% of the proof generation time for some like EVM circuit, also for some other circuit. But I would say like several months ago, we found out like using our FPGA system combined with a CPU where like you do all the MSNTT on the FPGA system, but you do some other components, some like previous minor components on the CPU. Actually, the percentage of MSN plus NTT in the ZK EVM circuit shrink to if I recall correctly, it shrink to like 3 to 4%. It's down from 60 or 70% like to 3 or 4%. So which means like if you want to have better performance, you need to accelerate other fluffy components in the latest generation. Yeah.
And so as you're working towards accelerating the, as you say, the fluffier components, are you marching down a path that is creating chips for specific protocols? Like, are you marching down the path of creating a KZG ASIC, or are these ASICs still like interesting primitives that can be built together into lots of different ZK protocols?
Yeah, so our current design can support KZG, Fry, Stark, folding skin, yeah, all these like major components. Yeah, so like we like yeah, so like if Cysic as a company just design a hardware for the KZG based one, or the for the or like more maybe like more generally for the elliptic curve based one, it will be actually like quite high risk for Cysic, as there are like a lot of like players in the market are using the Fry based ones, or like some other proof system. So like we try to support other proof system as well, like in our current design.
Got it. All right. So I want to shift the conversation here a little bit towards the process and the pain of manufacturing chips.
That's the pain.
So I think first, can you just give us a like brief overview of what does the chip design and manufacture process look like? Like, let's start from if I came to you as a company and said, I want to accelerate this this function, like how do you go from this is the goal to this is like what a design might look like to we've tested it, we know that it works, to like it's worth investing in a die, and then once you have a die, like how do you get it into like production and get thousands of chips?
Okay, yeah. So like the first thing is like we have a spec. So the spec like define the algorithm, the input, the output, and also the algorithm, and like then we write the RTO code for that. So basically, it's a hardware coding part I'm not very familiar with, but like this code, like it can be run on like FPGA and also on ASIC. We basically need to design, like we try to modularize the design, like to come up with some modularized part, like say like we can maybe divide the like computation into a lot of like subcomponents, and for each subcomponent we name it as a P, which is a processing element, the most fundamental module in the chip. And so like we can say and after we finish the RTL coding, then we will do some synthesizing on our end to see like what frequency we can run, like the higher frequency the better. Yeah, so normally it can be running at maybe 1.5 gigahertz or something like that. So so then we reach into a stage which we call RTO freeze. So like we freeze all this like front end code, and then we will work with like for startups, like if you are just maybe have around 20 people, you cannot afford to have a backend team in your to have a backend group in your team. So you will work with an external design service team who will convert your code into the real circuit on the board. And yeah, so the main goal of this like design servers is to improve the PPA, which is like performance, power, and area of your chip. And also they are so like since like we are basically working on the computation part, you also need to like integrate your computation part with like the IO, the external IPs. So like you need to go to like Synopsys or some other IP vendors to buy this like PCIe DDR IP, which is very, very expensive. Yeah, and after you buy the IP, like you handle your code, and also you are working with a backend design service team, like to get a higher PPA for your chip. And yeah, so that's the second stage. And at the end of that stage, you will have a GTS2. You send this like GTS2 to some fab such as TSMC or Samsung to do the chip tape out, which will be also very expensive, and you need to pay like you need to make the full payment in advance, like maybe 3 or 4 months ahead of time to reserve the capacity to do the chip tape out. Yeah, yeah. So after the chip tape out is done, like which takes also like several months to process, you get your it's like since like we are doing a full mask chip tape out, so we are going to get a wafer. The wafer like it has like a lot of like chips on it. Like we just cut the chips in piece, and then this come to the most exciting moments is to see whether you can bring up your chip, like whether your chip is like, fully functional. Um, so the bring up time takes like highly uncertain, maybe like 1 month, like to several months. Yeah. Yeah, if you are like very happy you can bring up your chip, then the next stage is to say you need to pack your chip into the PCB, which is the printed circuit board. Like you design your PCB and you have another like vendor in the supply chain to manufacture your PCBs, and also then you assemble the same thing into a machine, and then then fortunately you can dispatch your machines to the buyers. So that's so
Yeah, a couple months and many $1 million later.
yeah, that's like if you are lucky, then like yeah.
Got it. So to summarize what you said is you start with the spec, and then what you guys do at Cysic is take the spec, design it in software, apply that software to FPGAs to make sure that it works and that it's actually, legitimate. And then you ship off this design to the backend developers who will like actually take your design and like write out the silicon, write out the wires, like what needs to be done. That plan goes to the chip manufacturer, which, let's be real, is just TCMC right now. And then there's many substeps, but essentially they create the chip for you based on the design. It comes back to you. You have to test it, and assuming the testing goes well, then it's time to send it to consumers or to customers. Is that right?
Right, yeah. So like one more thing, like the thing like we are doing, like after we finish all the RTL coding, we need to basically like first run it like on FPGA and then on some emulator to make sure our design is correct. Like we also like play a lot with FPGA to explore the design space, like to get like better. Yeah, but the FPGA, so like yeah, we try some experiment on FPGA, but the FPGA, like if you want to try the experiment, like you also need to satisfy the resource like restriction on FPGA, so like it's kind of a headache, yeah, to get like optimal performance and also to make sure your design is like correct, yeah.
And so, as Cysic as a company grows, is the goal to vertically integrate more and more until you can do the entire design and then just give it to TSMC? Or do you really like sitting in the like space of the front end development of the chip and then working with the supply chain to make it happen?
Yeah, so I guess like in the beginning, which is right now, like we try to have the chip to go to the market maybe as soon as possible. So, which means we can only handle the design part. We actually we use FPGA to work with a lot of like supply chain vendors. So for the FPGA, we also like we have we have several customized FPGA machine, and the only thing that's not coming from us is FPGA chip, which comes from AMD, and all the other things, the PCBs, the machine, the cooling, the power delivery, all are like designed by us. And also we work with like supply chain extensively to make sure we can find reliable and trusted vendors to deliver the product like in time. So I guess like for now we rely a lot on the vendors, to do some manufacturing for us. Yeah.
But the goal long term is to bring as much of that in house as possible as you grow in bandwidth and resources.
Right, yeah. So actually, that's also something ongoing since like we are right now like working with like PCB vendors, and for some simulation, we actually like for the power for the heat simulation, we have to do it by ourselves since like our design is so specific that they haven't encountered something like this before. Yeah.
So, this question a little bit out there, but I'm very curious about manufacturing chips in 2023 because this whole genre is like kind of the molten core of a lot of the geopolitical tensions between US and China right now. And so I just kind of very broad question, answer this however you want, but do you find that the geopolitics in the news is actually creating enough noise to affect the way you're able to do business? Or is this, like many things, one of those things where there's the news version of the world and then the business version of the world, and they kind of operate non-interactively?
Yeah, so I guess like it's something in between. Like you need to be cautious about that. Like whenever like we want to work with some vendors outside the US, like we need to check with the export control to make sure we are compliant on that part. So yeah, and as you can see, maybe if you are using a very advanced node to do the chip tape out, maybe you have to wait quite some time for that. So like, which means like we need to shift our maybe chip tape out to some like more mature and less competitive nodes. Yeah, to use those ones. Yeah.
So, in this same vein, the United States, like within the last few years, has made a major bet on chip manufacturing. There was the CHIPS Act, which put like tens, if not hundreds of billions of dollars directly towards like new chip manufacturing or chip designing or chip anything in the US. One, is that something that's an opportunity for Cysic? But two, more holistically, do you see the US becoming an actual competitive place to do a lot of this chip manufacturing, or do you see this as kind of tilling at windmills and maybe a, a good idea, but like probably not going to make a real dent in how this industry works?
I will say maybe in the first few years, the maybe the chip manufacturer will still happen in Taiwan, as you can say, like the TSMC due to yeah. So like the US, like the chip factory in US, they need to do a lot of experiments. Yeah, so maybe I'll just use example here. Maybe it's not a very appropriate example. Yeah, so like when Huawei, so Huawei is a Chinese company who is forbidden to do chip tape out in almost everywhere outside China. Yeah, so they use like a Chinese chip design, chip like tape out factory called SMIC. So actually, the SMIC is like previously SMIC use a lot of like the mining machines to try their like process, try their techniques to make sure the thing like they try out they are like fully functional, fully correct. And after that, they will have like maybe after a lot of tryout on the mining machines. So like Huawei then come to SMIC to do the real chip tape out for their cell phone. So I guess like for the United States, yeah, so like I know some information like the chip design, chip factory in United States is going a very similar route. Yeah, it's using some mining machines to try their process, try their technique. Yeah, maybe after this like few years, like the U.S. chip factory should have the real capacity to do some very advanced chip tape out.
Got it. So you look at what's going on in the US and say, like, obviously it's chips, short term, nothing's going to change, but there's actually some like real reasons to believe that there could be like a renaissance and maybe a real decentralization of chip manufacturing globally.
Yes, yeah. Yeah, I believe that. Yeah.
I mean, listen, like the less like important TSMC is, like I think the less scary geopolitically the world is. So
Right.
very much a
Yeah.
fan of like new nodes in the chip manufacturing network.
Yeah, yeah,
Yeah. Cool. All right. So I think we've like covered what we can cover in manufacturing here. Let's like shift like to the little bit higher level of the stack. So I think we've talked a little bit about like we want to create chips in the end game that are accessible to hobbyists and to home people. So like let's talk a little bit about like the business you're trying to create, right? Is selling chips. Is there any part of you that wants to buy a bunch of your own chips and be a like kind of centralized proving farm that can be accessed like as an API, anything like that?
yes, yeah. So like we will also use part of our chips to provide the service to our like partners right now. So like we have a little bit more than 90 ZK project who want to use our servers, but right now due to our maybe shortage of GPU servers or FPGA servers, we can only provide servers to a handful of that. Yeah. But with our chip, maybe sometime next year we can provide the servers to all to maybe like we can account for a minor percentage of the computing power for all the ZK community.
Got and so when you're the customers that you're working with right now, do you have any benchmark of let's say that they had the world's best cryptographers, but like the world's most average hardware engineers and like infrastructure people, and they just implemented code on AWS in general in CPUs. How much more performant and how much better can you do than a kind of a naive implementation in that way?
I guess like it also depends on the circuit. Like for instance, like for the ZK GPT-2 circuit, which is by Daniel Kang, using like our FPGA combined with the CPU mode, as I mentioned before, like we run the major component on FPGA while all the fluffy component on the CPU, we can get a 50 times speed up over their like CPU performance. and the CPU is a 64 core CPU. So basically, if they use a CPU to run the ZK circuit, it takes more than 9,000 seconds, I think. And using our approach, we can reduce the proof generation time to 180 seconds. Yeah, so that's
Wow.
yeah, so that's one example. And for the ZK event circuit used by some layer twos, like we can easily get a 5 times speed up over their like GPU performance. Yeah. GPU performance is usually 3 to 5 times faster than the CPU performance. Yeah.
Hmm. And so this is with your current solution that is the FPGA plus the CPU kind of like hacked together version, right?
Yeah. That's right.
So once your chip is ready and you're able to install it in the system, like what do you expect the performance to be? Let's say on the ZK EVM one.
Yeah. So I guess the current. Yeah, we basically we want to generate ZK event circuit in less than 1 second. ZK event circuit in less than 1 second. We want to achieve real-time ZK proving. Yeah, so which means like all the major ZK circuit, the ZK EVM, ZK GPT-2. Not sure about ZK GPT-3 or GPT-4, but for ZK GPT-2 circuit, we can definitely generate in real time.
Got it. And this might be a little basic, but the important thing on the ZK EVM is that you need to generate the proof quickly enough and post it to Ethereum that like all the state changes that just happen on the L2 make it to Ethereum and not like 20 minutes later or 2 hours later or like some inordinate amount of time, right? Like that is the real impact that your technology can provide today, just like for the very few use cases of ZK that are in practice, right?
Right, yeah. And other than that, we have a few customers who are designing the ZK DEX, decentralized exchange. Yeah, so like in that case, I basically want us to generate the ZK circuit, ZK proof as soon as possible. Since maybe if you wait like more than 1 second, then the price will change, and yeah, and then you lose some of your money. So like that's another case. And there's like the ZK bridge and the ZK coprocessor, like who also want us to generate the ZK proof in a considerable sort of time. Yeah.
Yeah, I mean it's super interesting, and I think I'm a huge believer that when we get like 10 or 100 or 1000x improvements on efficiency, we like technologies evolve, right? And the best example is the internet, right? And
Right.
it's like we started with ARPANET, which is like literally sending single characters to each other, and then fast forward we have GeoCities, and then fast forward we have Instagram, and then like right now we are streaming high quality video, talking in real time, and it is that like order of magnitude improvement just in the like bandwidth that has like really transformed what the internet is capable of. And so with that, I'm so convinced that these order of magnitude improvements, like people like you and Cysic are making, or just the order of magnitude improvements people like Succinct Labs or anyone that's just helping developers abstract out all of this like complicated math, are going to provide these order of magnitude improvements that transform the technology. But the big question mark is what does the world look like when we can do ZK instantly and trivially? Like, have you really spun your head around on like in a world where Cysic is like this multi-billion-dollar behemoth and ZK compute is cheap and easy? Like, what kind of world are we living in?
Yeah, so like the ZK can basically so like ZK is somehow independent of the blockchain. So ZK basically provide a way for people to interact like it basically erase the layer of like trust. Like you can use like you don't need to trust anyone. You can use like you just need to trust the math. Like we can use the ZK proof to communicate without concerning about the trust behind the things. And also the ZK has a lot of like I guess like other than the blockchain world, ZK can be also used in the maybe traditional world. So the traditional work we can use the ZK to fight like deep fake. We can use ZK improve the TPS of some of these banks or some financial institutes. And also we can use ZK um, to make sure the traffic, the network traffic, they are satisfy the compliance using some ZK meter box technology. So I guess like with the powerful hardware, like we can find more applications of ZK that we probably like we couldn't imagine before. Yeah, so like for like as you just mentioned, like if like the with the improvement of bandwidth in the internet, we can right now have like Instagram or even like TikTok. Like like when I was like in Beijing 10 years ago, like I also start an application called yeah, it's very similar to TikTok, but due to the slow bandwidth at that time, it can only support Instagram. So like that startup was not a very successful one. Yeah, but like with right now the high speed, like we can do a lot of things, and also I believe with the high speed of the powerful ZK machine, we can also explore like more applications of that.
Yeah, for sure. And I know it's always like really tough to say like, well, what's going to happen once this technology is ready? I mean, if anyone had that answer, we would not be on this podcast, we'd be founding a company right now. But
Yeah, right,
I
yeah.
I'm just so convinced that like while the purpose and the energy around ZK today is about blockchain, I'm just looking around at the world changing and like what as AI gets better and every device out there becomes internet connected and cars are driverless and Amazon's delivering drones or sorry delivering packages with drones and like the world is becoming more connected, more digital, more autonomous and I don't understand how any of this is possible without some sort of coordination system. And I think blockchain is a huge part of it, but it's not the whole part of it. I think the whole part of it is cryptography.
I totally agree with that. And also, like, maybe one more reason to start Cysic is to say, like, I'm a cryptographer, and I know that, like, the cryptographers, they design, like, very elegant systems, like, there's, like, in theory. And this system cannot be deployed in the real world is due to the efficiency. And ZK is just one example. And we also have, like, homomorphic encryption and other things, like, yeah, so like maybe one personal reason to start Cysics to bring this like wonderful uh, crypto systems like to the real world. Maybe like previously like via some customized hardware, then like buy some like normal hardware. Yeah, so that's also maybe a personal reason like to start Cysics. Yeah.
All right, Leo, thank you so much. I mean, I could seriously go on for hours here, and I really would love to sit down with you and talk about like what the ZK enabled future looks like. But I think this is a good time to wrap it up. So, like before I let you go, can you just like let the audience know where can they find you if they want to learn more about Cysic? Where can they find Cysic? And like most importantly, like if you just want if you like us are understanding that ZK is not only going to change the world, it is like the um, shelling point of the next like just technology revolution. How do you learn more and how do you get involved in ZK?
Yeah, I think like the ZK community is a very friendly community. Like you can always try, you can always find a lot of like materials to learn about the ZK. You can always like type in awesome ZK and you will find a lot of surveys. Like a very long list of all the resources you need to learn to like to code like in ZK. Yeah, it's a very good community, and you can always find a lot of like YouTube videos online to learn about that. And if you want to find Cysic, you can just try to type in like Cysic, CYSIC, and maybe like our Twitter handle is like CYSIC underscore XYZ. So that if I remember correctly, yeah, that should be the Twitter handle. Yeah.
Great. No, thank you so much. So yeah, please everyone go check out Cysic. As I was telling Leo over the last few days, like the this Cysic is so important to what we're like what needs to happen in order to make ZK like a real usable technology and whether it's in just like making the performance good enough for enterprise applications or like I think even more importantly wrestling this magic math into something that's like accessible by people without PhDs is what I like to call the Lord's work. So I really appreciate what you're doing. I really appreciate what you're building for us. And man, I hope to stay involved and watch you conquer the world.
Thanks a lot. Yeah. Thanks for inviting me to talk about in the podcast. Yeah.
Of course. Well, Leo, thank you so much and have a good rest of your day.
Yeah, you too.